couldn't make to the meeting those kind of couple weeks before. So as organizer, we have to step in. So that's why you see a couple talks given by us. Okay. So today I'm going to talk about some work did on fractional order derivative-based regularization for restoration and image registration applications. I come from University of Liverpool, where I'm associated with the two centers. One is imaging techniques. The other one is this National Center for Mathematics in Healthcare, where we also do a lot of imaging. Okay, so as I said, I'm going to talk about how to use fractional derivatives in this context. First of all, look at the simple problem of image restoration, where you have some image and then it's degraded due to noise, and there are different noise models here. We're looking at additive Gaussian noise, and then so the given noise image here on the right, you want to restore the clean image U. And another related problem is image registration. These two are traditionally not related, but you can view it in a similar framework depending how you see it. So here, given a pair image T and R, you want to look for similarities or a transform phi that takes one to be close as possible to the other one. So this transform is a vector. It has two components. We talk about each. You can think of each component needs to be regularized, and we use fractional derivatives. So the plan for my talk is as follows. First of all, I just show you some sort of simple introduction into variational framework, and then I talk about this fraction order derivatives, and then I want to emphasize about how you define these regularizers formally, and then straight onto the algorithm, how you apply them. My main message for the first main message today will be if you haven't used this thing before or heard about it, fraction derivatives are quite friendly in terms of algorithm. They have a bad reputation because they lead to they're defined as like a sum. It's a non-local operator, but actually it's because of nice structure. They can be as efficient as the usual integer order derivatives. And the next thing I talk about is some brief description of some of the theories we developed for these models, and before some experiments. Okay, so this is the familiar part for all of you. So here for the restoration model, we normally have a data fidelity term and restore some quantity U, and then this regularized term RU. So for the data fidelity, and the two norm is very commonly used, and then you could use one norm depending on the applications, or fractional half norms if you want sparsity. This is used in the context of denoising here I mainly talk about, and can be used in deep learning problems, convolution, and tomography, where if you replace the k by a line integral. Okay, so I'm not going to talk about choices of data fidelities. I'm mainly concerned about choice for the regularizer. As you imagine, there are too many choices. We are spoiled choices. It's not possible to list all the people who have worked in this topic, because there are too many. I simply list a few types that are interesting. First of all, the familiar IOF, where you will penalize the one norm of the gradient, and then you have this fractional power of the gradient, where you want some other properties depending smoothness or sparsity you want to have, and then this second order information you want to regularize. And then these combination models, they are very robust, like the TGV, where you the E is symmetrical. It's also a gradient. And then you have this, you can do a decomposition model where you split U you are looking for into two parts. One part you regularize using TV, the other one using high orders. And then you can look at general convex function FG. You design them to have more robustness. So that early paper by Chen more than 10 years ago, that used that term alone, and it's very good for smooth images, but not so good for images with jumps. Now, and then more recently, there are quite a few colleagues working on mean curvature and elastic related or Gaussian curve related restoration. These are, if you look at the operators, they look a bit horrified, pretty bad. Like if you look at mean curvature square or modulus of mean curvature, and then the Gaussian curvature is too long to write down here, and the results are very good, actually. In many cases, they're probably better than the combined ones, but the solvers are really struggling. You have to work really hard to find effective solvers for them. Okay, there are some works already, but they are not quite sort of optimal. There's a more fundamental problem with this 7 to 9. The problem is there's not much theory. For example, I haven't seen any existing theory for the solutions. You can do simulations where you see, for example, the mean curvature model. It's very good for modeling solutions with jumps and also solutions with smooth profile. It's good for everything, but there's we haven't got a theory to prove that. Okay, and then this fractional one. It's a sort of slightly more recent development for imaging, but as a topic for fractional PDEs have been around for many years, too long. And then they have been found very effective, and because there are various definitions, boundary conditions, and people tried their own choice, and then there's no sort of systematic studies of this fractional TV. So this is where my starting point is. So let me give you the 3 common definitions, and then talk about some properties before applications. So the one here definition is the one most people use. This is the generalization of integer order derivatives. This is for order alpha for any alpha fraction, say 5.4 and 6.7 and so on. So it's just a bunch of coefficients defined by binomials G alpha J. And then this is for the one-sided. You can do the two-sided version. And then this is the backward. You can do the forward and so on. And then I want to show you the whole picture. So you see my color code here is to say for the Riemann-Liouville and then the capital. These ones, they are very similar. So what's happening is with the Riemann-Liouville, you integrate, and in this is my notation, for beta between 0 and 1. And then so the notation is alpha is arbitrary fraction. It's a real number. So you put it into 2 integers and minus 1. And then you either integrate and differentiate. It's an integer differentiation that gives you the Riemann-Liouville, or you differentiate first and integrate. That gives you the capital. If you look at this way, so the only thing you care about is this fractional integral. The rest are quite easier to see. Okay. And then, so as I said, these are defined for this interval A for some some point A to the current point T, where we are talking about derivatives. And then you can talk about two-sided T in the middle, and then you can look at the whole interval for any of the definitions. You can do this averaging. Okay. So what's important is their connections. First of all, for very smooth function, remember alpha is between n-1 and n. So if f is this much continuous differentiable, so the one without superscript, that's the Riemann-Liouville equals the GL derivatives. They are equivalent. And then for slightly less, f is from C n-1, and then you have this RL and then the computed derivatives. They differ by this much. So you can see clearly, so these guys are involving the boundary, the initial point on the left. So if the homogeneous, if these guys are 0, usually we assume they are. So these two guys are identical. So what does this mean? This means that's why in practice, when you discretize, you use the same formula. People don't bother about developing a new formula unless it's a special situation. Okay. This is an intriguing formula. I'm sure many of you haven't seen it. So what does it say? This you can talk about AB here. I'm looking at 0 to T. So this Riemann-Liouville operator can be written as infinite sum with this finite coefficient made of gamma functions an. Here I write down for alpha equal 1.6. What is it? So A0, you see the magnitude is minus something. They alternate, and then very soon they are so small, almost 0. So for this case, you might say 1.6 derivative is a combination of 0 derivatives plus first derivative, second, and third. And the rest are so small. That's intriguing. Okay, let's talk about the a formal definition for this fractional seminon. So here, assume again alpha is given. It's between two integers n minus 1. In practice, we use alpha between 1 and 2. So n would be 2, n minus 1 would be 1. And then, so here, this equation 2, I'm sure you can recognize this is just simple generalization of the TD seminon. And here, just use the alpha derivatives for the very smooth function k, which are so much differentiable. Okay. And then you can divide this BV alpha space as a subspace L1 when this seminon was less than infinity. That's the straightforward. Okay. I want to move on to how to compute, how to use these guys. So first of all, I give you a glimpse of why these guys are good. So here I'm showing a noisy signal, and it's like 1D signal like this. And the true signal obviously is like quadratic here, is constant and linear and so on. And then if you use the TV, we all know how to do it. It depends on how you tune the parameters, and then there's some, you have piecewise constant solution. Okay. So you can kind of approximate the quadratic part very nicely, also the linear part. The constant part, if you tune the parameter right, it's sort of good. But for the fractional model, you can see the smooth curves almost like restored perfectly. I have to admit there's a minor problem with actually constant, because the constants, unless you use the capital, are not preserved. In other words, the fraction derivative of constant is not 0. So that's why you can see minor oscillations. But the jumps and the piecewise linear, piecewise quadratic parts are very nice. So there's no staircasing effect. Okay, let's talk about this model and how to solve them. Right, so this is here, what we do is, I show you the general definition. This is the equivalent one if you assume this guy is slightly most more smooth. So you look at this alpha gradient, and then you do this denoid. So given Z, you want to find this U. Okay, so how to solve this model? We use the Bragg splitting. So in case you don't know, I just recap what Bragg splitting. So it's a kind of augmented idea. So here I'm talking about so the generic problem, you minimize this functional subject constraint, and then you use this this Bragg idea, and then you can add this. If you have the L1 norm, you can use this replace this difficult L1 term by this vector quantity, and then to simulate this equality. So that's the standard stuff we heard about yesterday. Okay, here we propose to use same idea to solve this fractional model. So how do we solve it? So first of all, we let D to be that fractional quantity, and then so that gradient is gone, and then so the one norm some norm modulus L1 becomes this L2, and this will make the resulting ER equations much easier to deal with. Okay, so now we have with this split variable D, we have two unknowns, D and U. So if you look at the two subproblems, so first of all, for the U problem, because of the L1, the one norm becomes two norm, so you have the linear fractional PDE. You can derive that, and then this is much easier. Subject to a nice conditions, this can be solved nicely. I'll show you some details. And then this subproblem D for split variable, this can be found analytically if U is given. So you alternate. Okay. So let me show you for this sort of linear PDE how you solve them in practice. So here I'm just showing you. They give the fraction derivative digitize the gradient, you get a dense matrix. Here I'm showing line by line. So here I'm to fix YL and look at x1 to fn. Okay, it's like horizontal whole line. Look at the digitization, and then for the whole domain x direction, x derivative, you look at this tensor product, and similarly for the y, it will the other way. And then you go back to the formulation. Okay, that's the coefficients came from this GR. This is from the GR digitization I show you on the early pages. And then you can actually digitize the divergence using the C derivative, but it turns out they are only order H difference, so it's no big deal. Okay. So if you put all these guys using finite difference into this formula, you get this sort of equation. And then what we do next is to rewrite them into a matrix form so that it's very compact. Okay. So you use the chronic product properties and so on. Anyway, so let me show you the final result. You can merge all these things easily. So when you merge them, what you get, eventually you get something like this. So B is the one of the block for one line, okay, and then you get this U, capital U is the little u grouped in a matrix, the original image matrix form, not the vector U form. So this guy is just like this dense structure block topless matrix, and then this is the Sylvester form you get. So why do I talk about this? From this equation, you see it's computational, in storage-wise, it's no big deal. Why no big deal? Remember, for this each little b is only little n by little n. Okay, the image size n by n. So this guy is also n by n. Okay, so not n squared by n squared. Okay, so this storage is no big deal. And then if you compare this with deep learning, if you think about that, it's much harder This is quite easy to process. So here we use the country gradient type of method to solve. And then start another problem, and then you can do the multiplication very quickly because they're topless matrices. Okay, that's one part I want to emphasize. Also, these eigenvalues of that matrix, you can bound them using the property using simple Cauchy-Green theorem. Actually, I'll skip that. Okay. Right. So that's the algorithm for this part. So the main message I want to give you is it's because of the structure matrix, it's quite easy to solve. Now let me talk about briefly how do you use the idea for image registration. There are two applications I'm thinking. The one is a naive one. Okay, for image registration you have two components. You can split. These are displaced. My notation earlier phi. Remember, earlier on, I was saying given two images T and R, so the registration is to find this phi function, which is vector, and here we write as x if there's no displacement, they are identical, plus is u vector. Okay, such that find this one such that. And this is T phi approximate R. Okay, so that's the image registration problem. So here I'm writing a formulation for displacement. So the displacement you use the fractional these semi-norms. You want them to be minimized, and when you want the least square fitting. Okay, so that's image registration. So I call it naive application because if you have a favorite regularizer for the U1, U2 to regularize separately, you can apply them using TGV, using mean curvature, using you just use TV H1, whatever you want to regularize. That's a simple way to do it. And also you can do a more sophisticated one, something I've been doing very recently. So how can you make it complicated? You want the components of this U1, U2 component, you want them coupled in some way. There are many ways to couple. This is to borrow the idea from color image regularization. So here I'm just showing one choice depending on how this W subspace is chosen. So I'm showing like you can think of like a vector version of the TV alpha definition. So you want to choose this is W like this type of products, and then this is how you regularize the vector field U, and then you can define a space like this for these vector guys. Okay, and then if you do that, so you minimize this, if you like, vectorial fractional derivatives. And then this is the usual fitting. And then we have some algorithms solved by augmented logarithm method and design a min max solution. Okay, so that's a more sophisticated version. I've skipped that. Okay, let me talk about how much theory we have developed for this problem. First of all, go back to restoration, I have two problems. For the other one, we just worked out recently, and so you go back to this problem, and you can show using the space we defined dB alpha. You can show through this usual usual tools, starting with compactness, lower semi-continuity. You can show this guy has a minimum in the dB alpha space if the coupling parameter is given. For image registration with the space, I didn't show the slide. With this space, we construct a VBV alpha. You can show the solution with our scheme with this model, you can show the solution also exists in that space. Okay, let me show you. Oh, maybe I show the say one remark before I move on. There's somewhere I didn't highlight a lot. I mentioned so far. I want you to get with the first takeaway message. That is, the non-local operator part is not a problem in algorithm because the structure matrix can be done very efficiently. The second message, this functional, functional is convex with fraction derivatives in the right space. When it's convex, and then the result competitive to harder models, so it's a very good candidates for different applications. So convexity is a nice thing. Okay, let me show you the first set of results for the image denoiser. So here I have the very relatively smooth penguin image, and then so I want to restore from the noise F, and then you compare TV. You see the quality got patches, and the mean curvature could be quite smooth. Smooth solution probably over smooth, and so this Fractional approach quite competitive with TGV. Obviously, if we try to tune with TGV, the two parameters A and B, isn't it? You have the first order term. You can also make a TGV loose by tuning the parameter the wrong way, but so we try to several sets make sure it's best. Otherwise, it's not fair. With this one, the only choice will be the fractional power. So we just fix for all our experiment 1.6. So it's also some advantage there as less choice. Okay. So visually, they look very similar and close to TGV. But if you look at the PSNR table and SNR table, we have a few more. I'll show you one experiment. We have a few more experiments. You can show obviously, you may say PSNR is not a good indicator for comparing quality. It came out pretty good compared to TV, and way better than the TV and the mean curvature. So they are kind of close, they say. Okay. So this bit I just really emphasize my message. So the storage is not a problem because it's we are not talking about n squared, but n squared matrices. We talk n by n matrix B, and then that's we just need to store that one. Actually, we don't need to store it if we solve it by iter solvers. You just need a multiplication. So storage is not a problem, and then use the circulating to approximate. The only thing we haven't done is the preconditioning for the CG solver. But otherwise, if you look at CPU increase for different experiments. So here, for the first case, I take the image 128 square up to 2048 square on a laptop. And then you see so you probably don't care CPU, you see how the ratio increased. So the ratio about 3 something, 4. Okay, so as the number of pixels increased by 4, the CPU is increased by 4, 5. So it's almost optimal, it's not multi-level. Okay, so it's that's, you see, what's the reason? The reason being, there's not much to store, and then, so so the scheme is already quite quite useful. So here, C case, I use the capital digitization formula, the minor variation, order H difference, and they come up really similar. The quality-wise, all very, very, very similar. Okay. So that's just re-emphasize the efficiency. Okay, so here I'm showing you a few results for registration. So so I want to evaluate how good it is. So first of all, I want to check this T-minus fidelity term, how much it has achieved that as SAD or relatively comparing before registration. You want to drive that to 0, but in practice you can't because this for some problems, well, for most problems, you want the regularity. Okay. You also check, make sure this Jacobi matrix is not negative, otherwise it's non-physical. So this is how we sort of implement the model, and then near the end, we check the quality of solution to see at which points this might violate. If yes, it's not a good solution. Okay. So I just got this simple image to show you. So here I have a slim hand, this is a bit fat one, and then you want to sort of shrink the fat one into the slim one to see how the deformation is found by different methods. Here again, I use alpha equal to 1.6. So you compare with the elastic models, a linear curvature, a mean curvature, and this fractional one. So they are given slightly different indications. So obviously, when you see a small SAD, you think that's really good. It depends how much whether so actually here you see the visually mean curvature does look slightly better than say the first one definitely got a bit not quite correct elastic because second order information is missing. So this is SAD and the part of story. And then if you look at the mesh quality, you zoom in one important area in the middle, you see these methods, and then they do have folding. In other words, visually you are cheated. You see, it looks a beautiful result. You can register this to that. But in practice, the problem mesh cross each other is completely wrong solution. So this one, the fraction one, doesn't fold for this case. Okay, and then possibly the best model in the literature is with a hyperelastic model by Martin Berger and Siski, their group, and then we compare with that's available in FAIR. It's updated. So it's so we compare the hand image with their image. So we have TV, diffusion, mean curvature, hyperelastic. So they look sort of similar. Actually, FAIR is slightly better for this particular case. But you see that mesh quality is slightly different visually. Okay, so this one is slightly more smooth. Right. So I gone a little bit fast. So I want to do a quick summary. So fractional order variation provides a new regularizer, and then it's a non-local regularizer, which can be considered for many applications where you have to regularize. And then it has some clear advantage I want to emphasize. Convexity. If you in the right space is convex, therefore you can design good algorithms, apply some other algorithm, and show the theory. Without convexity, some of the method can't be applied, so it's been a problem. And then it has the ability to compete with higher methods. So this is between alpha between 1 and 2 is once more than 2 is like a high order, and so this to compute high order sort of okay. So it's we also tried with some comparisons with non-local TVs. It came out a little bit better. Future works. I think fast solver, although we sort of through CG and this second matrix and the techniques and this Sylvester equation stuff, we use all the big ingredients, popular ingredients, split recommend, and then topless circular matrix techniques and country gradient. This sort of combination of nice ideas. We make the fast already, but I think it should be faster. And positivity constraint we have put in. We have for the registration, although we don't see a folding for the audit experiment, but we have no explicit folding control unless hyperelastic model. But I think why not? We should consider. But I think folding control makes the solver really complicated, I have to say. And then boundary condition not convenient. So I didn't mention a lot of boundary conditions. There are two things we could do. One, so far, you estimate the boundary behavior of solution, you subtract the thing out. Or you just assume I have a zero Dirichlet and zero non-invariant boundary conditions. So we probably need a better theory to overcome the boundary. So that's the weakness. So this is not the end of the story. So, what I said so far is to tell you the current status with this modeling. Can you do them more? In other words, forget the traditional framework. Can you design using fractional derivative, design some really good algorithm or theory to compete? Try to the best. So I think the something you can do is you don't. I think no one says you should compete the fraction with the integer. Why don't you mix them? So I think this is one possible idea. So the distributed order fractional derivative is sort of popular last 2 years, 2-3 years. Is one idea is like this. So you think of a range you're talking about, say 0.5 to 2.5 or whatever. You say I'm going to use all the partial derivatives, okay, including integers. So in other words, you're not saying, you guys there, I'm here, let's repeat. You can't win, okay? You can't win, join them, kind of thing. So there are definitions like this. Alpha, you choose a different range, including integers. And then there was this paper by Chen and F. Deng in inverse probe imaging, where they done this in sort of in a selective way. They say, okay, let's not this integer, let's pick two guys. Say this is, let me think, they tried 1.8, the other one 0.9 or something. And they also tried 1 and 0.9 and so on. Try two fractions or two numbers and just see what's like. It seems the result really quite good. And I think I don't, it's not a criticism. I feel the boundary condition with this model, you got a problem if you think about it. Say you take alpha 1 to be 1, alpha 2 be 1.6. Then you see, how do you define the boundary conditions? With the integer u, you normally for imaging expect what you call Neumann or some not zero Dirichlet. But this one you need a zero boundary condition. In other words, a complex boundary condition. I think they just, I don't know, somehow they just did it, assume all zero or something. But actually, the examples, they don't have zero boundary condition. But anyway, the results are quite good, actually. So there's something along this line. I think there's something we are doing right now is to see, go back to the, you remember for the integer case, where we have in the early slide I showed you, you want a quantity u to be regularized. Why don't you split in part? Some bits you want to regularize using one fraction, including integers. The other part you want to use something else. Therefore, you have your own boundary condition. As long as you add it up, the boundary condition makes sense. I feel that's a much better, neat way to deal with boundary conditions rather than somehow try to force them. Maybe I stop here. Thank you.
There are several definitions of fractional derivatives, but the most naive way would be just to perform Fourier transform and then just everything is done, right? Is there any difference between all these definitions?
You're right. There are too many definitions. I think the ones the Fourier one is a mystery we haven't tried. Because the Fourier ones, I'm not sure how you deal with the boundary conditions. But so here I think our model covers these three types, GL, RL, capital. So we look at the equivalence and then, but the Fourier ones, a couple of people mentioned that. Because the Fourier, somehow you feel the computation is already, somehow it's implicitly easy somehow because it's through Fourier narrative. But I feel need a bit, we need to look at that in details.
Another question, yes, please.
So very interesting talk. I was wondering, about your fractional divergence or fractional gradient. I mean, is it? It's homogeneous, but is it rotation invariant? Which may not be completely obvious because the gradient is rotation invariant, I mean, if you do a second power, it's also rotation invariant, but the fractional.
Good question. I think, well, because we choose alpha more than 1, also because the equivalent with the capital, I think the might be, well, possibly. Okay. Good question.
And the other thing that puzzled me a little was your claim of unicity. Like, okay, so maybe it's just because when working with L1, usually, I mean, it's not strictly convex. So, okay, maybe I'm naive, but because you had a theorem where you said it was unique, the minimizer.
Yes, that's true, yeah. That's in the, for the image denoising.
Okay, I know more the case of, let's say, finite number of measurements and things like that, and there I'm sure it's not unique. But unless you have additional conditions. So you're sure it's unique, the minimizer?
Yeah, for the continuous case, yeah. For the continuous, yes, but for this discrete case, you need an extra condition.
You know, it's just because it's not strictly convex.
Not strict, yeah.
No, the discrepancy term is strictly convex because you don't have a linear operator with a kernel, so that's what gives you uniqueness.
Yeah, but I mean the minimum is unique, but there may be several solutions. At least, I mean, I'm pretty sure. Like maybe here it's because you have infinite measurements.
Yeah, sure.
But if you have finite measurements, it's not unique enough.
That's a different problem.
Yeah, but it's the concrete problem. You never have infinite measurements.
Yeah, but if you have finite measurements and finite degrees of freedom for the reconstruction, then you have a unique reconstruction again. It's the same number of freedoms.
Maybe, okay.
I think maybe for deep learning, I did show we mainly look at the denoising where the blur operator is identity. We have deep learning, maybe it's.
Yeah, so
yes.
I think this may be correct. Like if you have like as many measurements as unknowns, then I think.
In your test, is there an adaptive way to choose the alpha?
No, we just fix it, and then
How do you choose it?
we just fixed 1.6. It seems like a good lucky number, but in practice, they're not. We don't know enough. But I think people usually have an intuition saying if you choose alpha close to 1 because you want the solution close to TD like. Because analytically that's true, but also if you want a smooth solution, you want this guy closer to 2. But there are no theoretical studies about that. This is like intuition.
Okay, final question is, in your numerical example, how you set your boundary condition?
0.
You just set 0. So,
0 traditionally 0 Neumann.
okay. So
Yeah.
because you haven't shown the deburring case, so I think you
That's right. That's right. That's I think for the restoration, we have a way to deal with the non-zero boundary condition. That's in our the assignment paper. So what we did was we first do the one time. So you have so it's like even this one, it's not a zero boundary condition. We can clearly see not a zero boundary. So what we did, we first look at the noise image, and then restore the outform boundaries. You have to do the one-dimensional restoration. You assume that's good enough, and then analytically subtract from this fractional thing. Otherwise, the definition is like not satisfied. Yeah, it's a good point.
Okay, well, I think we should stop here. Thank both speakers once again. Thank you very much.